Here's a brief example that focuses on calculating concentration of certain solutes in solution and also reports them in terms of parts per million. So here's the problem. We have a local Superfund site that claims that the water is too caustic. A local plant is dumping 100 gallons per hour of wastewater into this stream, and this wastewater contains 50 kilograms per hour of sodium hydroxide and 50 parts per million of arsenic. Now, as an engineer, your job is to neutralize this waste stream before it's dumped into the environment. So to neutralize it, you'll use hydrochloric acid, since the product of NaOH and HCl is water and sodium chloride, and we could remove the sodium chloride if necessary. It's also important to determine if the amount of arsenic is beyond safe limits for the wildlife and the environment. Now, we're told that beyond 5 mg per liter of arsenic is dangerous for fish, so we need to relate the 50 parts per million to some kind of mass concentration here at 5 mg per liter. So speaking of that, let's do a quick review of concentration. Now, a mass concentration is just a mass per volume. So our mass of our solute per volume of our solution. So maybe we'll see this as grams per liter. Now, if we talk about a molar concentration, this is moles of our solute over a volume of our solution. So maybe we'll see moles per liter. Now, the term molarity is used when we use gram moles. So if somebody talks about the molarity of a solution, that's when we use gram moles and liters as the units of measurement. So a molarity of 1 means 1 gram mole per liter. And this is important here because we're neutralizing a base using an acid, just like you did in chemistry with titration. So we have a reaction where we have hydrochloric acid being mixed with our NaOH in solution. Again, these are both aqueous solutions, so I'll designate that with an AQ. This goes to NaCl, aqueous solution, plus water. And recall when we did titrations, assuming equivalent volumes, a 1 molar solution is neutralized with a 1 molar solution. So using that information, let's determine our molarity of the sodium hydroxide in the waste stream. So we're told that we have 50 kilograms per hour of NaOH, and that's in 100 gallons per hour being dumped into the stream. So let's first convert the 100 gallons per hour into liters. Now, to do that, we need a conversion factor between gallons and liters, and we could look that up and find that we have, for every gallon, 3.79 liters. So this gives us 379 liters per hour being dumped into the stream. So now we have a volumetric flow rate. We need to figure out the amount of moles of NaOH we have within that fluid. Now we could use the conversion factor of molecular weight to go between mass and moles. So the molecular weight of NaOH is 40 grams per mole. I'll write the molecular weight of HCl up here as well, since we'll likely need that later, and that's 36.5 grams per mole. So now to use that, we want to translate our 50 kilograms into moles. We divide by the molecular weight. I'm going to write 40 kilograms per kilomole. And this tells us that we have 1.25 kilomoles per hour, or 1,250 moles per hour. So recall, to get the molarity, it's just the amount of moles per liter. So we have 1,250 gram moles in 379 liters, since we're using a basis of an hour. This gives us 3.3 molar NaOH. So we have a 3.3 molar solution of sodium hydroxide. So we need a 3.3 molar solution of hydrochloric acid to neutralize this stream. Now there are a number of ways we could approach this engineering problem. We could add the HCl directly to the stream to form our 3.3 molar solution. Another option is we can make a 3.3 molar solution of HCl and add an equivalent amount, which means 100 gallons per hour, to our other stream to treat it. Problem with this is now we'd have 200 gallons per hour being dumped into our stream. And another option would be to use a concentrated solution of HCl and use less volume. So similar to option 2, but we would calculate how much we would need to add based on the molarity of the HCl solution that we make. So for simplicity purposes, let's just do option 1 and add the HCl directly to the stream. So how much HCl do we need? So we have 3.3 molar HCl. If we multiply by the molecular weight of HCl, which was 36.5 grams per mole, this will now give us a mass per volume, because here it's moles per volume. And when we do this, we get 120.5 grams per liter. So now we need to convert this into kilograms per hour of HCl that we would add. So let's multiply that by the volumetric flow rate. So 120.5 grams per liter times our volumetric flow rate of 379 liters per hour. And this gives us roughly 45.7 kilograms of HCl per hour. Now notice I converted between grams and kilograms without showing the conversion factor. So this answers the first part of how much HCl we would have to add to the stream. Now part B asks about the arsenic. Now so how does 50 parts per million of arsenic compare to 5 mg per liter? Now, generally when referring to parts per million in liquids, the general rule of thumb is that for liquids we think of a mass ratio. So a parts per million means 1 part mass per 1 million parts mass. So in this case, 1 gram of our solute per 1 million grams of our solution. So 50 parts per million of arsenic means we could write it as such. 50 times 10 to the minus 6 grams of arsenic per 1 gram of our waste stream. So we need to convert this into a grams per liter. So we're assuming our waste density is roughly 1 gram per milliliter, so that of water. So we could use the density to convert the 1 gram of waste stream into a volume. So if we multiply by the density and convert from milliliters to liters, we get 50 times 10 to the minus 3 grams of arsenic per liter. We could also rewrite this in terms of milligrams and see that we have 50 milligrams per liter of arsenic, which is greater than the 5 mg per liter for our cutoff. So this is dangerous, or can be depending on how diluted it becomes after being dumped into the environment. Remember, this 50 mg per liter is what's in our waste stream, and if it's being poured into a river, we would at least need a dilution of around 10 to get that down to a safer limit. But then again, anytime you use the terms dumped into the environment, it's probably something that should be given some thought.